In the last bit of equilibrium, we will learn about what is called the Chatelier's principle. It's a very interesting concept. So what is Le Chatelier's principle? Le Chatelier's principle is when you have an equilibrium and you change something like the temperature, pressure, or concentration in that equilibrium, then that equilibrium is going to shift in order to accommodate that variable or that change. Okay, so depending on what kind of an equation you have and how many things are involved in the equilibrium, these changes here with the temperature, pressure, and concentrations can bring about a change in the equilibrium, which means that, remember, your equilibrium can go forward or backward. So you can actually control that. And in some cases, we're talking about things that happen naturally. So if something happens naturally, then how is the equilibrium going to be shifted? Just as example, there is an equilibrium of carbon dioxide in this world. So that carbon dioxide equilibrium can be shifted by the concentrations that either we produce or we consume as a society. Okay, so that is, Le Chatelier's principle. Let's look at an example. So here is COCl2 to give us carbon monoxide and chlorine. So the question is, predict the direction of the reaction when chlorine gas is added to the reaction mixture, and then predict the direction of the reaction when carbon monoxide is removed from the mixture. So let's look at both of these things. All right, so the first one is when chlorine gas is added to the reaction mixture. So if you add chlorine gas to the reaction mixture, you're adding to the product side. If you add to the product side, that means that you have more of the products. So if you have more of the products, you will shift the equilibrium on the reverse side to form more of the reactants. Because at equilibrium, remember, your forward and your reverse reactions have to be the same. All right, and so if you have an imbalance of the reactant or product, the equilibrium is going to compensate for that. So if you added more chlorine, your equilibrium will shift backward. Okay, all right. So the next question is, predict the direction of the reaction when carbon monoxide is removed from the mixture. If you remove some of the carbon monoxide, now the concentration of this is less, and if this is less, then the equilibrium will compensate by moving forward. Okay, so that then again the forward and the reverse reactions are in equilibrium. All right, so very simply said, if you have an equilibrium and you add the products, you will make the equilibrium shift backward. And if you add the reactants, you will make it go forward. That is how the change in concentrations will affect the equilibrium. So in case of equilibrium of gases, gases are dependent on pressure. We know that already from our gases chapter. So in this case, the pressure and volume are kind of connected to each other, okay? Because of course gases exert pressure and pressure is dependent on the volume. Remember, it's an inverse proportionality according to Boyle's law. If you increase the volume, you decrease the pressure and vice versa. So here are the possibilities that we have, okay? So when the size of the container decreases, so when the volume is decreasing, the pressure is increasing. So if the pressure is increasing and the volume is decreasing, the reaction is going to shift to reduce the pressure, which means that it will shift towards the side where there are fewer gas molecules. Fewer gas molecules because the size of the container has decreased. All right, so there is not enough space anymore. So it's going to shift towards wherever there are fewer gas molecules. So here I've written it in one kind of line. Hopefully it helps. If you have a lower volume because you have a higher pressure, your equilibrium will go towards low moles, okay, of reactants or products, wherever it is. When the size of the container increases, the pressure is going to decrease, which means that if you're decreasing the pressure, you're increasing the volume. So in this case, now your reaction is going to shift to increase the pressure, which means that it will shift towards the side where there are more gas molecules. Why more gas molecules? Because now you have more volume. Okay, that's how I think about it. So if I have more volume, then I can have more gas molecules. All right, so which means larger volume, because there is lower pressure, will go towards, the equilibrium will go towards more moles. Okay, whether again it's reactant or product side, it depends. In the event that in the equilibrium, you have the same number of moles of gas in the reactant and in the product side, then the pressure will have no effect. Because even if you change the pressure, you're changing the volume also on both sides. and so it doesn't have any effect because the number of moles are equal on both sides. So it's only when the moles are not equal on either side, that's when you have the forward and the backward reaction. So let's look at this. Okay, we have 3 examples here. So which direction which each of the reaction shift if the volume of the reaction is increased. So volume of reaction is increased, meaning that pressure is decreased. All right. So here we have the first one. Here you have carbon monoxide and hydrogen to give you methanol. So here we have a total of 3 moles. Here you have a total of 1 mole. So more moles over here. If the volume is increased, which means that I can produce more of this, which means that my reaction is going to shift to the left. Okay, my equilibrium will shift to the left because my volume has increased. So I can make more of these. Okay, at this point, that is how I think of it. Okay, all right. So here in the next one, where we have 2 sulfur dioxide and 1 oxygen to give 2 of sulfur trioxide. So here again, the number of moles are more on the left-hand side. So if the volume of the reaction container is increased, then again, my equilibrium will shift to the left because the number of moles are more on the left-hand side. Let's look at the last equation, COCl2 to give carbon monoxide and chlorine. Now the number of moles are more on the right-hand side. So if you increase the volume of the reaction container, it will now shift to the right because there are more moles on the right. So it's very simple. Just keep an eye on the number of moles, okay, of your reaction system. That's it. But don't get tricked. If they're the same, then there is no change. Equilibrium and enthalpy. Okay, so we've covered concentration, we've covered pressure, and the last one is, of course, temperature, all right, which is the enthalpy. So the changing of the reaction temperature will change the value of the equilibrium constant, which is why when you look at the Kc expressions, most of them are given to you at a particular temperature, all right? So the equilibrium constant changes. So because of that, okay, because there is a shift in the equilibrium, that is why the equilibrium constant changes. Why is there a shift in the equilibrium? The equilibrium shifts because it is dependent on the enthalpy of the reaction. Enthalpy of the reaction is 2 kinds, okay, where you have an endothermic reaction and where you have exothermic reaction. So in an endothermic reaction, what happens? Endothermic means that heat is a reactant. Why? Because the heat is being absorbed, right? In endothermic reaction. So if heat is being absorbed, heat is the reactant. So which means that if you increase the temperature, you're adding heat as a reactant. So if you add heat as a reactant, your equilibrium is going to shift forward, okay? If you decrease the temperature, which means you remove the heat from there, it means your equilibrium will shift to the left because now it'll have to compensate for that because the heat was part of the reactant. In case of exothermic reactions, heat is the product. Okay, so because heat is given off, it's an exothermic reaction, so heat is the product. So which means if you increase the temperature, you're increasing the heat on the product side, which means that the equilibrium will shift left. If you decrease the temperature, you're removing the heat from the product side, so equilibrium will shift forward, okay, to compensate for that. So that is how equilibrium will change according to the enthalpy or temperature. So here is an example. Oh, look at this poor equilibrium arrow. Anyhow, so here is an example. If you have this equation where you have water of gas going into give water in gas form giving hydrogen and oxygen. The delta H for this is plus 484 kilojoules. What would you expect for this reaction to be favorable at higher or lower temperature? So here is your enthalpy of the reaction that's given to you. All right, so what I would do is I would rewrite this equation. Now I can use my equilibrium arrow and rewrite this equation to include the heat. And I would include the heat on the left-hand side because this is an endothermic reaction. It's positive. So it's an endothermic reaction, so which means the heat actually goes into the reactant side. So if it's at the reactant side, how would we see this reaction happening? At a higher temperature or a low temperature? Think about it. When the heat is added, you're adding more of reactant. So if the reactants are added, you will shift it to the right, which means that for this kind of a reaction, heat is good. Okay, so that's what's going to favor the reaction to the forward side. And so that's what it means, favorable, meaning to the forward side, not to the backward. We don't want reactions to go backward. You want them to go forward. So if you add more heat, it goes forward, okay, because that's the reactant. So here is your Le Chatelier's principle, all in one table. And so here, I made this myself, okay? So hopefully you'll understand it, and then you can write it yourself also if you want. So here is conditions. If you have reactants in there, when you increase the reactants, you will shift the equilibrium forward. If you decrease the reactants, you will shift it to the left side or to the reactant side, all right? If you increase the products, if you increase a product, then you shift the equilibrium to the left-hand side. And if you decrease the product, then you shift it to the right. So all the things that we talked about so far, they're all given over here and then some. So for example, we've talked about these 3 or 4 in the slides before. Okay, so you can look at that again here. The ones I want to talk about these are these last 3 here. Catalyst. If you add a catalyst, there is no change. Why? Because you're increasing both the forward as well as the reverse reaction. All right, so both of them will increase. This is a trick question most of the time. Solids, again, no change. Solids don't affect equilibrium. They were never part of the Kc equation, so they will not affect the equilibrium as well. Adding an inert gas, it doesn't cause any change. Why? Because the volume changes for the entire reaction, not just one side. So unless you're changing a reactant or a product, that's a different thing. But if you're just adding an inert gas, it's not going to make a difference. Okay, so these last 3 things were not covered before. These 3 or 4 were. So make sure you go through all of this. So here is an example, okay, and an equation is given to us, methane plus water to give us carbon monoxide and hydrogen. Assuming the reaction is initially at equilibrium, indicate the direction of the shift, left, right, or no change, okay, for all of these different conditions. So let's go through this one by one. This is the kind of question I would give you in an exam, for example. So if water is removed, here is the water. Water is on the reactant side. So if water is removed, then your equilibrium will shift backward to compensate for that. Okay, so which means your reaction will move left. If the temperature is increased, this is an endothermic reaction. Endothermic meaning that heat is on the left-hand side. It is a reactant side. So if you increase the temperature, you also increase the reaction, which means that it goes towards the right-hand side. The quantity of nickel catalyst is increased. Nickel catalyst, I can't even see it, but it doesn't matter because it's a catalyst, which means that no change, okay, for this one. An inert gas is added. Again, with inert gas, it's going to add on both sides, which means this is the whole reaction vessel. So if it's adding here, it's going to change both of these sides, which means again then, yep, no change. Hydrogen gas is removed. Okay, so hydrogen gas is removed. Hydrogen gas is a product. So if you remove this, then yes, all of these reactants are going to compensate by forming more product, which means it moves to the right. The volume of the container is tripled. So the volume of the container is tripled. Now you have to look at the moles. On the left-hand side, you have 2 moles. On the right-hand side, you have 4 moles. All right. So if you increase the volume of the container, you can accommodate more of the product. So which means that your reaction will move to the right because you have more moles on the right hand side. Okay, essentially this is a nice, good, full example of Le Chatelier's principle. So your key concept in this one is to learn about the Le Chatelier's principle and then predict the directions of the equilibrium. Or on the other hand, I can actually give you a reaction and ask you to predict what will make this reaction go forward. So in which case you have to think about all the conditions that can happen, which is the reverse of just the previous question that we did. Okay, so you have to then give me the conditions. So really quite easy, quite fun to do.